Okay, I'm hoping that you'll cope with this one remotely. Yeah, I'm just kind of feeling like actually if we do a bit now, then there's a bit more revision time before your mock, apart from anything else. So give you something to do as well, won't it? So forming differential equations for rates of change. And again, most of the time we're looking at areas and volumes, possibly a perimeter, but normally we're looking at sort of shape and space with these. So as an example, we have a cube of side length x. And the volume increases at a constant rate don't overly worry about units. You might, well, you need to make sure they match possibly in places, but centimetres cubed per second. So that's the rate the volume is increasing at. And we want to find dx dt when x equals 4. So this is actually really similar to what you did before, but you just need to do a little bit more work with it. Whenever you're looking at a rate of change, so this is a volume increasing at a constant rate, this isn't a rate of change, and this is talking about how quickly it's increasing with respect to time. And so dv dt, so the change in volume with respect to time, is equal to 0.024. So it's increasing by 0.024 centimetres cubed per second. So if you think about your units, the time is underneath. And then, as we did before, we're looking for dx dt, but we just need to work with what we've got. So I know that the volume is equal to x cubed. And this is really typical. If you're told something about the volume, you've got some dimensions, chances are you're going to have to find the volume, in this case in terms of x, and differentiate. And so dv dx, because it's in terms of x, is equal to 3 x squared. Now have a look at what I've got. I want dx to t. I need my dx on top, but if I do dx dv times dv dt, they're going to cancel down and leave me with dx dt. So I hope you've got the hang of that from that first sheet. So dx dt is equal to dx dv times dv dt. So two changes here is writing this down and just finding an expression for the volume and differentiating, and then you slot it together. And so dx dt is equal to dx dv, so that's 1 over dv dx times 0.024. This isn't lending itself to nice exact numbers particularly well. When x is equal to 4, that's assuming we're working in centimetres, because this is in centimetres. So just watch your units in this sort of situation a little bit. So when x is equal to 4, dx to t is 1 over 3 times 4 squared times 0.024. 0.024. I did this one earlier and it's 0.0005. I don't think that's rounded, but you might want to check that. That's the answer from my notes. I was going to do a tiny bit more. So rate of change in surface area. So we're still on the same cube. I'm going to do one more example. I think I might run out of time if I'm not careful. So B, rate of increase in surface area S when x equals 4. So this time we want the rate of increase in the surface area S. So we want, you just make it quite clear to yourself what it is you're looking for. We want ds dt. And we know that S is the surface area. So that's 6x squared because there's 6 faces of area x squared. So it's that same start, ds dx is equal to, sorry, I wasn't concentrating, that ds dx is equal to 12x. And so ds dt is equal to ds dx times by dx dt. So I don't need to do anything with inverting this one. ds dx is 12x times by dx dt, which is 0.005 when x equals 4. So I can substitute that straight in. And so I'm doing 12 times 4 times 0.0005, and you end up with 0.024. This is the rate of change in the surface area, so it's centimetres squared per second. But again, you don't need to worry too much about units. And yeah, I didn't think about it here, but when x equals 4, dx to t would be centimetres per second there.